Okay, maybe Xuan, you mind to introduce the speaker for today?
Okay. So can everyone hear me?
Yep, I think so.
Okay, good. So so for today's seminar, we would like to welcome Dr. Feng Ling from the Institute for High Performance Computing in A-Star, and also an adjunct assistant professor at the Department of Physics, the School of Humanities and Science. So I heard that they changed the name because after they merged the two faculty. I got to know Feng Ling a while back, while he was at the last stage of his PhD. He did his PhD in NUS on econophysics, which is an area that I still work on, but sadly he doesn't anymore.
Slightly, yeah.
Yeah, slightly. Okay, yeah. So he invite. I think he has been searching around in Singapore for someone in econophysics. So he found me. He invited me to his thesis defense. So I went there and got to know his work. And I realized that he also worked with Gene Stanley, who is in Boston University, someone that we both know. And then after that, I think he went to A-Star to join the Institute of High Performance Computing and continue working with Gene Stanley, but this time around on networks. So,
password is unique for everyone. It's different.
Oh, okay. So
maybe you can mute your microphone.
Okay. So then I think only in the past few years that Feng Ling has gotten into machine learning, because it is a hot thing to do. So obviously, because of his physics background, he started understanding machine learning from a physics point of view, and has gotten very interesting results. So I have heard part of this talk before when we invited him earlier to NTU, but to the Complexity Institute. But apparently he has done much more since then. So let's welcome Dr. Feng Ling to tell us more about optimal machine intelligence at the age of chaos.
Okay, thank you, Sion. Yeah, it's a privilege to speak here. Yeah. So today I'll be talking about this topic. I guess from the title of it, it sounds interesting. Yeah, let's see how much interest it is. I mean, so in my talk, if you have any questions during the talk, you just feel free to unmute your mic and ask me. You'll be fine. Yeah. So before going to the heavy part of the talk, let's just look at some videos. So this is a simple logistic map. So we are all familiar with logistic map, right? It's a quadratic map. But the thing is here is we do like 100 layers of compositions of that, which means you just look at an input x0 and look at what the x100, the 100th iteration as output, what it would be. So you put the output input map, you can see a clear phase transition, not just one. So you have what, like period doubling, then you see that. So you have stable periodic cycles until like it gets into some chaos. Of course, it gets into periodic doubling again in some places, but it's mostly periodic cycles. It's mostly chaotic after the first onset to chaos. So you can see a transition from stability or order to chaos, right? So now I'd like to talk to the outline of the talk. So briefly, I'll be talking about some background from actual neuroscience. Then there's the empirical evidence that we have gathered for machine intelligence. Now we're talking about some theories and the universality of the theory. And of course, if time allows, I'm talking about some of the recent results from ours to see how this theory can help in terms of the application to deep neural network trainings, followed by a summary slide. So let's start with the brain. Okay, so all this actually started with brain quite a long time ago. But if you look at the recent 2019 Turing Award, which is Nobel Prize for Computer Science, you can see that this is the official transcript during the awarding. So inspired by the brain, So the awardees, Geoffrey Hinton and others, propose artificial neural networks, right? So actually they are inspired by neurons, which means the connections and the nonlinear activations. So this is a microscopic scale of how the brain works, and the machine artificial neural networks was inspired by it. So, but as P.W. Anderson has mentioned, more is different. A single neuron doesn't give you intelligence, but a lot of neurons in the brain give intelligence, but more is different. So what is this difference that give rise to the so-called intelligence, or in a more like probably a scientific way in this context is like information processing capabilities. So then there's been a lot of empirical evidence over the past several decades talking about emergent critical phenomenon in the brain. So it's basically when they talk about critical, they measure a lot of self-similarity, they might measure a lot of power law distributions, long-range spatial temporal correlations. Yeah, so these are all signature of a critical phenomenon in the brain. So it's from neuroscience. So then there are a bunch of people who has been first pinpointed as like to point out that this phase transition, the critical phase transition, is not between any two phases, but it is between a specific set of phases, which is order and chaos. So so there has been a lot of effort trying to understand it for like the neural networks. So before the deep learning era, there has been a lot of work attempting to understand the neural networks like simple architectures. The first one was started with in 1988, where there has been some proofs and empirical evidence showing that a simple neural network with random connections exhibits chaos. And there has been some simulation evidence showing that actually the edge of chaos, which means if you see this at the edge of chaos between order and chaotic, if you measure the information content, if you measure the information transfer, they are maximal. So, and there also has been some preliminary theories about why this happens, why this information content is good for this kind of random neural network single layer construct. So okay. So if you just think back about neuroscience, we know that criticality, like phase transition, usually gives scaling relations, spatial temporal long-range correlations, or in other words, power laws. But we know that if you just observe a power law, which is typically what is observed in the brain, it doesn't necessarily, I mean, some people will argue that it doesn't necessarily give you, it means criticality, right? So the good thing about artificial neural networks is really you can pinpoint whether or not it's a critical phase transition and the nature of the critical phase transition and why it is so. And also the good thing about deep learning now, or artificial neural network now, is it has evolved tremendously in the recent years, so that in some of the applications, in particular computer vision, it has matched the human level recognition somehow. So it's time to, and the other thing is you can really observe, unlike biological neurons, you can manipulate every single neuron, every connection, and you can observe each one of them in real time. So, and essentially that's what we do. Okay, I would like to go back to this again, some of the logistic map, 100-layer logistic map you have seen before. So it has only one parameter, which is kind of the weight in a neural network, and there's nonlinear activation because it's a quadratic function. So you do observe, as I've shown before, you did observe like a single state, stable state, to like periodic cycles that increases with cycle length, and its cycle length is the maximal at the edge of chaos, then it goes into chaotic phase mostly, right? So I'm showing this because actually, okay, this is what essentially happens. This R is the single parameter, which is essentially equivalent to a weight in the neural network. You can see the simple stable point to periodic cycles, periodic doubling, then you have like mostly chaotic phases. So I'm showing this because I want to plot this diagram where, so if you plot the time evolution at a steady state, so this is what you observe, right? A single stable point. So the blue point is the original input, where the x0, x prime is the perturbed input. So at a steady state, you can see the two input, they become the same. But as you increase the weight, the number value of R, so you can see a periodic doubling, and the perturbed value in the long-term evolution, it goes to the same value as the original value. But in the, so same thing goes for the like a 4-period phase. But if you go into a chaotic phase, you can see the 2 points are almost scattered around randomly. So they are effectively deterministic chaos. So you can see a clear phase transition from a single stable point to periodic doubling to chaos. So the interesting thing that you can observe in a neural network that is trained on one of the benchmark data set is essentially you get the same phenomenon. So here we have a multi-layer perception, which is one of the more primitive models that's being used. So it is trained on this benchmark data set. It's called the fashion eminence. So there are basically 10 types of fashion wares you need to classify them into. So this is a model that classify into. So if you extract this, the bulk of the neural network, and use it as a dynamical operator, you do observe actually a strikingly similar phenomena as the logistic map, which means like at the beginning of the training, when you initialize the model leads to a single stable point. And as you train more and train more, you have like double cycles, you have 4 cycles, and then you reach a chaotic phase. So whenever you see the orange dots and the blue diamonds are not overlapping, it means chaos, because their initial condition only separated by a tiny bit, but eventually their asymptotic behavior just scatter around, not overlapping. So this is actually trained like on with a real network and with a real benchmark data set. So it's a strikingly similar phenomenon here. So yes, also you can also plot the Poincare plot, right? I mean, some of us must be familiar with this one. So you plot xt plus 1 against xt. So if you have only 1 point on this plot, you have only 1 stable point. You have 2 points, it's usually like periodic cycles of 2. Then here at close to the edge of chaos, you have a lot of points on the Poincare map. Each one of them represent a point on the periodic cycles. Then when R value is huge, close to 4, you have things just randomly scattered around. It's deterministic chaos. So this is the edge of chaos, at least we call it, I mean, it's the first onset to chaos around 2.56, 2.57. So you can do the same thing for the previous example where you have a neural network, multi-layer perception trained on one of the benchmark data set. You see that as your training proceeds, you evolve from the fixed point to a smaller periodic cycle, to a larger periodic cycle, to a very dense periodic cycle. It is still a stable periodic cycle because you can see the orange and the green, they are still overlapping, right? Until epoch 7, the stability collapse, or it becomes unstable, it becomes chaotic. You can see there's a scatter around the Poincare plot becomes a densely populated set, and the 2 points just get far apart. So this is there's an empirical signature of chaos. So, and then the next interesting thing is the previous neural network model I've shown you. You can see that, okay, from left to right is the training time. So the more you train it, the model will be in different phases. So from left to right is you increase the training duration. And so the blue is order phase, the green, the background is the periodic cycle phase, and the chaotic phase is the orange background. So if you just plot the chaotic map at each epoch during the training processes, you can see that it follows the process of phase transition single stable point, periodic cycles, and chaos. So this quantity, I'll talk about it later. This is a theoretical quantity. Essentially, when this quantity is equal to 1, is the edge of chaos.
Can I just ask a question now?
Sure.
Maybe we get very confused.
Right, okay.
In the perceptron model, what is X?
So the X, okay, the X is the image, is the input image that you see.
Okay, but the input image is a matrix, right?
It's a matrix, so we cast it in an arbitrary direction.
It means what? You project it onto
a fixed direction. Right. Right.
Okay, so that the direction is random or chosen in some specific way. So
we chose it in a way that is the average of the, so each point is a vector, right? So we chose it to be the average of all vectors, but so that the visually is more resolved, but you can choose almost any arbitrary direction. It doesn't matter. It just like they may be like not so much visually resolved.
Okay.
Yeah,
and
that doesn't matter.
Okay, so in the periodic phase and in the periodic part, you can see 3 ring-like structures, right?
Yeah.
So does that mean that it can identify 3 types of APROs from the the APRO MNST database, or so is the number of rings corresponding to the number of types of APROs, or this is nothing to do with the category of the objects in the database?
We haven't checked that, but that's a good question. Yeah.
Okay.
Yeah.
Okay. So yeah, sorry to interrupt. Yeah.
Yeah, no problem. That's a good question. I mean, it's for clarity. So yeah, so you have this periodic phase. So you can see that this gray line is the loss function. So the test loss function, not training loss function. So you can see that the minimum test loss function happens at the edge of chaos, which means the model transitions from the periodic cycles to the chaotic phase. And the test accuracy is saturating at this edge of chaos point. It barely increases. In some cases, it decreases actually. Yeah. So so that's the takeaway here. Actually, for this simple model, the edge of chaos corresponds to the highest accuracy, lowest loss, which means it's optimal, right? So how about the other state of art, which means more complex or complicated deep neural networks on other benchmark data set and with the state of art training algorithms and techniques. So there's a bunch of them. So the first one, the next one we tried is, so this another data set is CIFAR-10, is also one of the most popular benchmark data set that everyone uses, and use convolutional neural networks, which is basically there are convolutional kernels. It's making the model more complex. Essentially, you see the same phenomenon. So you see that actually, so this, we have only 1 ring. So you can have 1 ring or 2 rings or 3 rings. Yeah, it depends on your simulation runs. So you do see the same thing. The test loss is minimal at the edge of chaos, and the testing accuracy is saturating here. And okay, this is something I will come to later. So this is a theoretical measure of where edge of chaos is. It's when it's 1, it's edge of chaos, so it's also here. So you essentially get the same thing, right? So then there are even more complicated models, which this is actually, we can say, this is state-of-art models, one of the state-of-art models for computer vision. Basically, you have skip connections, they create the residue connections, you have, so we use ReLU activations, which is part of it, and Adam optimizers, we use data augmentations. So all the state-of-art techniques we use on it. So we see how it behaves. So there is regularization here as well. So which means we try to use the regularization techniques that people use to prevent overfitting. So interestingly, you can see that this model, it starts in the chaotic phase. So then, so you can see here it's in the chaotic phase, right? So as you train the model more and more, because the model prevents overfitting, so you can see the test loss gets lower and lower, right? And the accuracy saturates. And the interesting thing here is once you reach about epoch 350 around there, it leaves the chaotic phase. It oscillates between the chaotic phase, periodic cycle phase, and fixed stable point phase. So you observe here, actually, if I only plot 3 for illustrations, but if you really look at the process here, it just keeps fluctuating among these 3 phases. Actually, this is evidence that some interesting evidence that the periodic cycle phase is extremely narrow. That's why the system can hop around it so frequently. So, but anyway, you can see that actually the state-of-art machine learning models with their training techniques actually pulls the model close to the edge of chaos as much as it can. Yeah, and as the model, you see, because it prevents overfitting techniques, so you can see the model barely overfits, and the test accuracy just saturates, gets slightly, like incrementally, marginally higher and higher, about 90%. So this is another model, that's DenseNet, which is somehow has performance similar to that of the previous one. So just to be thorough, we test this as well. So it exhibits a similar phenomenon. So closer to the edge of chaos, it leads to higher accuracy. I mean, I don't mean it's causal, but phenomenologically, this is what we observe. And also, after some epochs, about 40, it starts to oscillate between the 3 different phases. So, okay. So, of course, the next question is why the edge of chaos? So let's just look at some theory. So, for infinite dimensions, let's say you have infinite number of neurons per layer. So we also call it thermodynamic limit. So ergodic theory basically tells us the deterministic chaos is equivalent to randomness. So you can also just write it down. Say the steady state of this dynamic operator is X star. So you can write in terms of, say, the mean of it. You can say it's a deterministic mean, and the random part of it, which follows a 0 mean, right? So sigma is the amount of randomness or the standard deviation of the randomness mean. So what chaos essentially says is when this sigma transitions from 0 to now larger than 0, it becomes chaotic, because when it's smaller than 0, you have no randomness. So essentially your steady state is a stable state. So, okay, then naturally we'll think of a Landau theory of phase transition, where say if this is order parameter, it changes from 0 to larger than 0. So you have a phase transition. So that you solve that, it gives you this. This is basically the square of the F norm, at the Jacobian matrices of the Jacobian matrices at the steady point, the asymptotic points. So F is essentially the operator. So if the normalized value, which means 1 divided by n is dimension of the system, is 1, that's the edge of chaos. So then from random metric theory, actually, we know that if this is 1, because J is a Jacobian matrix, if this is 1, essentially you have the spectral radius equal to 1, which means the maximum eigenvalue of it is 1. The radius, I mean, the modulus of the maximum eigenvalue is 1. And when this is 1, which means actually you are at the edge of local stability. So in the thermodynamic limit, edge of chaos corresponds to local stability. But then we also know that actually the real neural networks, no matter how many dimensions it is, no matter how close it approaches the thermodynamic limit, is finite in dimension, right? So if you remove this thermodynamic limit, you can see that there's another, probably not that well known, at least to me, initially, result in random metric theory that if you lower the dimension, actually the spectral radius is way beyond 1. So you can see if it's the matrix is like dimension 4, the maximal eigenvalue is about like close to 2. But if you increase the dimension of the system, actually it's only at infinite dimension this thing holds. Which means actually at finite dimensions, when you're at the edge of chaos, your spectral radius is larger than 1, which means you are locally unstable, but you are globally not chaotic. So that naturally gives you periodic cycle as a bifurcation process. Which, yeah, edge of chaos doesn't equal to edge of local stability. So yeah, so this actually, yeah, I was talking about is a Neimark-Sacker bifurcation. Is essentially the discrete version of topped bifurcation. Gives you periodic cycles, and the larger is your spectral radius, naturally it gives a larger period. And a larger period means on your periodic cycle you have more states, and each state can represent information, right? Because usually the basing of traction will attract the surrounding inputs to this particular states. So yeah, this is essentially a copy from Wikipedia. Apparently Wikipedia has a lot of good animations to see. So you can see there's a lot of states, periodic states, but then later it gets chaos. So as your rho gets larger, the periodic cycle gets larger as well. So it's true for the one-dimensional logistic map. It's also true for high-dimensional systems. The only difference is that for logistic map, okay, let's here. Maybe let's look at the graph and talk about it. So the edge of chaos maximus. So why edge of chaos is good? Because at the edge of chaos, you have maximal spectral radius before things get chaotic. That's why you have maximal number of periodic states. That's why it's good. So mathematically, these 3 states are defined as the stable fixed point state, phase is when spectral radius is 1, and your normalized Jacobian metric, Jacobian norm is also less than 1. So this you are locally stable and globally ordered. So when you're locally unstable, when you're globally ordered, you have this periodic cycle phase. And at the edge of chaos, the rho is maximal, so you have longest periodic cycles. Of course, the next phase is both are larger than 1. So you're locally unstable, you're globally chaotic. That's why you have chaotic phase. So you observe this in a one-dimensional quadratic map, logistic map. You also observe in actually high-dimensional neural networks. The only difference is that you can look at this phase diagram. The dimensionality affects the width of your periodic cycle phase, because it's what we talk about the random metric theory at higher dimensions. Essentially, these 2 conditions become so close together. That's why you have this. So yeah, so in neural networks, you have a very, very narrow, not even just neural networks, actually probably like for generic nonlinear dynamical operators, you have this very narrow periodic cycle phase. It's easy to miss actually, but yeah, it is there. Because of high dimension, that's why it's easy to miss. So I guess I have some time to further talk about some of the latest things that we try to extrapolate the theory to the deep neural network training. So essentially, they start with looking at the hyperparameters of the training algorithms in deep neural networks. And putting a compass here is essentially because what we're trying to say here that north is edge of chaos. So now we know that where you need to push your model towards to. I mean, previously, the deep neural network training is just mostly, I say mostly, there are other theories as well, but I think mostly people are just looking at the accuracy and loss. But now we have more like a theoretical intuition on where you should push the model towards to, and that is edge of chaos. So what people do in deep neural network training is to find in the minimal loss function. And one of the basic algorithms to do that is stochastic gradient descent and with momentum. Of course, this one they call SGD, and with momentum. There are other derived training methods, but they're more complicated. So here for illustration, we only show this one of the simple and widely used method. So eta is called learning rate. It's essentially how fast. So this is a loss landscape. So eta is telling you how fast you are going down the landscape. And B is batch size, which means is each time you only put like 10 or 20 samples in your training. You can put the whole sample, but usually people don't only put a subset for various reasons. And also there's a momentum, which means you memorize the previous gradient to accelerate to make your your path more directed. So this one over alpha is kind of momentum, we talk about it. So these are the three major parameters that people use in the training. So then, okay, now to illustrate how to do this, we use a single hidden layer. It shouldn't be called MLP, multi-layer perception, but just let's take it this way, with tangent activation. So we don't use the state-of-art activation because we want to draw equivalence to the SK spin glass model, because there's a lot of theoretical intuition and result we can use for that model. So we use this model. There's only a single layer of hidden layer, has the same number of neurons as the input layer, which is number of pixels for this data set. We still use back this data set, this one, the benchmark data set again. So it's fully connected, so you can see, look at the weights, right? So usually people initialize the weight randomly. The weights also appear to be randomly distributed in the end after the training. So you can say, okay, the weights Jij is normally distributed with a mean J0 and the variance J square scaled by the size of the system. So this is somehow equivalent in theoretically to the I just S and K spin glass model. So this is not the exact illustration of the model. I'm just giving the intuitive thing because this is on 2D lattice. But actually, this model means every spin can interact with any other spins in the system. So just like visual illustration. So these weights in the model is essentially the coupling strength between spin sites in this SK spin glass model. So in this spin glass model, we know that there is paramagnetic. Of course, there's a ferromagnetic that's outside of the phase diagram. I don't plot it. And there is a spin glass phase. Theoretically, so this actually, the order phase is equivalent to the paramagnetic phase. I mean, at least the boundary is the same. And the chaotic phase is equivalent to the spin glass phase. So this is where you initialize the model at. Then you keep training it for 500 epochs. So you do see that actually the model evolves down. Actually, yeah, in the previous spin glass research, people already learned that actually it's just lowering the temperature as you train it. As you optimize, minimize the loss function, you are effectively, analogously decreasing the temperature of the system. And so you actually transition from order phase to chaotic phase. So somehow when you're close to the edge of chaos, this is somehow optimal, gives you optimal accuracy for the model and optimal loss for the model. So, so the goal here is without regularization, the model will just overshoot optimal and overfit. So of course, we don't want to prevent overfitting, right? Not only we want to prevent overfitting, we want the model to only stabilize and saturate at the edge of chaos. So, so if you really observe, look into the three parameters I was talking about in the order phase. So, okay, so the horizontal axis is the scaled epoch, which means the training time. You can scale the epoch with these three parameters. Then you can see each line is a different training algorithm, which means it's the same training algorithm, but with different set of values like this. So you can see this is order phase because J square is smaller than 1. So within the order phase, actually things scales linearly very nicely together. In the chaotic phase, things like you have local minimums, you have things like that, things gets problematic, so things don't really scale, at least not scale in this way. So, but the good thing is we don't really care that much about chaotic phase, right? Because the more optimal is at the edge of chaos. So things do scale linearly. Okay, so this picture basically tells you that actually all these three parameters, training parameters, you can tune them in whatever way you like, but actually they are somehow associated with each other. So yeah, so this is kind of a physical picture of what these training parameters are about. So if you, each line is the loss function for each of the training path. So you can see if you scale this training time, actually they also collapse over into each other. So that essentially means that actually it doesn't really matter what's the value. Of course, you change to a very drastic value, like if learning layer is insanely high, you won't reach here for some other reasons. But here we're just saying that usually for a set of training parameters you tune, you can just change them so that you reach the optimal the fastest. But then I haven't talked about how do we constrain the model to, saturate, don't go over. How constrain the model that when it trains, it reaches the optimal, and it forever stays the optimal. It never goes in chaos or never go into order. So how do you do that? So there is a regularization technique that's also commonly used. It's called the weight decay. It's essentially L2 regularization, or in more plain language, is to penalize the square sum of weights. So when the squared sum of the weights are too large, you only penalize in a loss function. So given the previous linear scaling relationship, A is the slope of the previous plot. So you can actually theoretically derive like what's the good value of this penalization constant that will make sure your model stays near the optimal point, which is edge of chaos. So we calculated that this lambda should be larger than 0.0005. Then empirically we observe that, okay, it's slightly larger than this, but the order of magnitude is about the same. So if you set this lambda to be 0.009, which is less than twice of this lower bound, your model actually evolves and it keeps staying there at the edge of chaos. But if your regularization is too high, you regularize the model too much into the order phase. In this case, it's also no good. The accuracy is actually lower. But if you, this is the orange line. So if you don't, this is no regularization. So it goes into the very chaotic phase, which is here. It is no good. Yeah, you can see the accuracy is marginally smaller than the edge of chaos. But if you over-regularize it, use a very huge penalty on this, and then your system will be over-regularized, your actual performance will degrade. So the red line is here, you regularize so nicely that it just saturates at j squared equal to 1, which is the edge of chaos. So this actually, usually people set this number arbitrarily to see when it performs the best. So here we have some intuition by how you should best set this regularization term, which is what we call a compass. Okay, with that is my last slide. So to start, just the summary of it is the biological and artificial intelligence are both at the edge of chaos due to the largest information content, the largest bifurcation cycles. So of course, with the artificial neural net models, it's easier to find like more deeper or more concrete evidence than the biological neurons in general. So metastable states are key to learning, to understand what is knowledge by learned by AI. And of course, I just illustrate one, how you can actually have applications from the theory to do how to principally control the training algorithms and to control chaos. Potentially it can maybe help in, say, maybe architecture designs or other things for a neural network. So that concludes my talk. If you have any questions, feel free to ask. Yeah.
So, any questions from the audience? No?
Maybe I have a question.
Oh, young boy, yes.
Hi.
Hey, young boy.
Yeah, I'm just trying to understand. So basically for the examples you have shown, the optimal results of the training occurs at the edge of the chaos. So am I right to say that when you are in the ordered phase, in the non-chaotic phase, the accuracy of your neural network is really bad, but deep in the chaotic phase, it is overfitting, then the performance is also suboptimal. So I think the accuracy is still quite high, but I think what you're trying to say is overfitting in the deep in the chaotic phase.
Yeah. So actually, you're right. So in the order phase, the accuracy is lower because it's underfitting, and in the chaotic phase, the accuracy is not that bad. It's overfitting, but it still learns something, right?
So by seeing overfitting, you're basically saying the loss function is increasing a little bit.
Yeah, so you're right. So the loss function in the overfitting case is increasing. Yeah. So actually, your model gets less Yeah.
less
Stable.
predictive power. Is it so from the accuracy point of view, since your test result is still quite good, so what is the reason why we don't like the neural network deep in the chaotic phase?
Okay, so we also did another set of experiment.
Right.
So you're talking about these points, right?
Yeah, these
Say
points.
This point. So these points, although they have a similar accuracy, but if you perturb your input image, so you add some noise to input image, their accuracy drastically decreases.
I see.
So that is also not desirable, right?
Okay, I see. But at the optimal point, it's more stable against perturbation.
Right, it's more stable against perturbation because there's no much chaos, right? Here it's too chaotic. That's why.
I see.
Yeah.
Okay. Maybe just one follow-up question is: have you ever seen any example where you can have very good performance of the neural network, but the network is in the ordered phase?
Yeah, we do see that. Actually, when your model is extremely over-parameterized, which means your data set is simple, but your model has extremely a lot of weights. So you don't need to be at the edge of chaos. You can capture the complexity of the data inside order phase because you have more than enough weights. That's why.
Right.
Yeah.
But at the edge of the chaos, do you see overfitting as well for those examples?
Okay. Do you? Actually, you do. If you define overfitting as the gap between, so this, you can see these two accuracies, right? Training and testing, right?
Right.
So actually in the order phase, the gap is the smallest. Some people define overfitting as this gap.
Okay.
Yeah. So in that case, the order phase is always better.
I see. So the more you train, basically, the overfitting will be more severe. That's in general.
Yes, that's in general. Yeah, that's in general. Yeah.
I see.
Yeah.
Okay.
So it's kind of a compromise, actually.
So there are examples where the optimal point can occur in the ordered phase, and also it can occur at the edge of the chaos. Are there also examples where it can occur deep in the chaotic phase? I'm just trying to see how general.
That we haven't seen.
I see.
Yeah, the chaotic phase is usually not. Yeah.
Okay. Thanks.
Yeah.
Well, I guess I have a cheeky question.
Okay.
So can there be overfitting in the human brain?
Of course, you hallucinate, right?
That means that we study so hard that we get chaotic.
I mean, we sometimes
or is there something like the the regularization that you tested, that we after we learn we kind of stay where we are, we don't go crazy.
You mean in the brain?
In the human brain, yeah.
I mean, okay, I only have some like a layman guess of this such things because I'm not really a neuroscientist.
Yeah.
So I think about brain definitely overfits. We sometimes associate things for wrong reasons. I mean, yeah, that's definitely. I mean, that's one way of overfitting, right? I mean, things are not really associated, but we force association between them, right?
So I guess this kind of overfitting can then manifest themselves as a cognitive dissonance. It means after you accepted a model, right, you refuse to budge from the model. So every other case that fails the model, you just ignore them. So
yeah, it could be. And also, if you look at the theoretical perspective, so this is the let's say this is equivalent to the standard deviation of the strength of the neurons, the wirings, right? So usually when the standard deviation, which means if the neural connections is not so strong, you are in the order phase. If it's too strong, you are in the chaotic phase. So maybe when your brain is overly hyped up, active, your connections are keep firing here around, you are essentially in the chaotic phase. You can make wrong connections, like overfitting your thinkings here and there. Right? But I mean, I guess probably that's where my outsider understanding, that's where like your sleep helps, because when you sleep, and also neuron degeneration helps, because when some neurons degenerate, and when you sleep, basically the strength maybe gets weaker, so it pulls you back to the order phase, then you actually get a more sanity and better understanding of what the outside world is really is, right? Maybe. Maybe. So essentially, yeah, the order phase in the brain is somehow like in this theoretical picture, it's like the neurons are overly active. The strength of the connections are too strong. So by reducing that, it helps. Yeah.
So any other questions from the audience?
I have a question. I mean, so if you study deterministic chaos, somehow you can, I mean, using complex mathematical model, you can go back to the dimension of the chaos. So how many, I mean, what is the space that you need somehow for this chaotic to occur? I mean, do you have this kind of similar information here? I mean, can you extract some kind of dimension of the system? Or?
So yeah, I guess we are talking about the various the dimensional measure for chaotic states, right? Like information dimension and things like that, right?
Yeah.
We didn't try that. Yeah, those are mostly in the chaotic state, right? I mean, in the order phase is probably dimension less than 1. So
right.
So at a transition, I suppose at a transition is between 1 to 2. Your transition from, I mean, here you look at it, if it's a periodic cycle, then dimension should be less than 1, right? So the transition probably also refers to when you are transition from a dimension 1 to a dimension higher than 1 into chaos. But we didn't really think about the dimension at each stage in the chaotic state. Yeah, we didn't think about that. I think it can be studied empirically, like especially information dimension, you can really empirically measure it. We haven't thought about the theoretical way of dealing with this. But it could be interesting to look at as well. Yeah.
Okay, thank you.
Okay. So I think I have further questions for Feng Ling. So let's thank Feng Ling. Don't know how to. I mean, we can clap, but I think.
Yeah, I can hear it. No problem. I can hallucinate to make my brain chaos.
Yeah. So I guess David will have some administrative things, instructions following this, right?
Not really. I mean, the next talk will be next week, so there will be some announcements. So
okay.
Nothing special to say.
Okay.
Okay. Thank you very much.
Okay, thank you. Thank you, Sion and David.
Yes.
You're welcome.
Bye.
Yeah, nice talk.
Bye.
Bye.